Good afternoon, can you hear me well? Great. So, welcome to the AWS Big Data Demystified meetup. The purpose of this session today is to share with you the experience I had of working on AWS on big data products. It was a long road and the amount of technology is quite vast, so the idea was to prepare some sort of knowledge transfer to share with the community what we did, what we chose, why we chose, and to give some sort of a map of or an index of the ecosystem. This is not a lecture per se. Please feel free to share, ask, interrupt. It's basically for you, okay? So just so you would know, I would send for the meetup organizer the slides and the video if everything will be okay. And I also put it on my website with other lectures and blogs, so you can search it and search other content that may fit your needs. Okay, so this lecture, let's start with the disclaimer. I'm not trying to sell anything. I'm not a sales guy. I'm a pure technical guy. As I said, to transfer some knowledge. You're more than welcome to challenge everything I say. I'm not trying to teach. I'm just trying to share what I did, what worked for me. This lecture was created in mid-2018, so things change over time. So maybe in 2 years, if someone watches this video, things may change. So basically, what is big data? From my perspective, big data is when the data outgoes your ability to process it. So there are about 4 V's that usually help navigate the use case. What is the volume? Please. The volume of data per day, the velocity of the data per second, the variety of the data sources, if it's JSON, CSV, events, and the veracity, how much the data is accurate, which is also a problem. In the past, talking about big data was a bit simple. Most apps were treated as application. You had a web server, an API behind it, a database, and some data warehouse behind it. Nowadays, about 10 years, 15 years later, the ecosystem has exploded non-linearly. I mean, it has become too complex to master all the tools available in the ecosystem. And it's become a craft only to navigate through the different tools to understand the advantages and disadvantages of each technology and what is good for you or your company. My perspective is that it's become so big, one man cannot handle everything. You simply cannot know everything, at least about this picture, and this picture doesn't even represent the entire ecosystem. Simply what we had to encounter in Walla and decide whether we are going to use it or not. So I removed some of the things we didn't use and left only the things we did use. And then this is how AWS treats the marketing side of everything. It takes a lot of these technologies and wraps it in a platform as a service, mostly called EMR. So everything becomes much more simplified when you work in the cloud compared with an open source solution or a distribution like Cloudera or any other Hadoop distribution. So let's talk generally, what's the challenges of creating a big data architecture? The first question you need to ask yourself, what is the business use case? how fast do you need the insight? I mean, it makes a difference if you want the insight within 15 minutes to 24 hours. If you need it less than 15 minutes, you could do it in a batch, meaning files and another file and another file, and pay for the penalty of window of how much time it costs to transfer the file. You could use streaming, which is per event. I get something, I know something about it, I can do something with this, and so on and so forth. And it really depends what you're trying to do behind it, what kind of insights, how complex are the jobs, or call it the insight you're trying to achieve. Velocity. There are many ways to cut the levels of velocity, but let's say under 100,000 events per second, it's not a real problem with today's technologies. Over 1 million events per second is costly, but it's doable. Over 1 billion per second, it's not trivial at all. Not a lot of use cases justify such an ingestion problem, but I've been talking about this use case with some friends. Volume. I mean, nowadays, talking about 1 terabyte of data per day, it's not a problem. Over it really depends on what you're trying to do. Over a petabyte per day, well, it really depends. Really depends what you're planning to do with the petabyte. And the veracity is quite as it used to be: CSV, JSONs, XML for semi-structured, and unstructured data, which is pictures, movies. When you talk about veracity, it's very important to understand the structure, if it has a structure at all, some sort of structure, if it's a nested structure, or it's completely unstructured and there's no way to model it with SQL. So basically there are many follow-up questions, but these are the big ones. What are the performance targets? How fast do you need to process the data? The cost targets. 1 second, please. Need to fix this so I will be able to track the video. To see there's audio. I sometimes mess up with the audio, so sorry for that. Security restrictions. Some companies have regulation on the data and how they can process it. For instance, privacy. Which technology to use? Are we going to do it on a data center or a cloud? It's a completely different technology stack. Even if you choose a different cloud, different technology stack. What is the latency? What is the throughput? How many users are going to work with your platform concurrently? Any access pattern? Should you restrict something? Are you going to use platform as a service so you can use more technologies because it's simple? Or infrastructure as a service, just put your technology on a server and let it run. As a rule of thumb, in terms of architecture, you should decouple everything. Whatever you can do as a separate unit, separate logical unit in your architecture that has an input and an output, do it. You can no longer break it into two, it's decoupled mostly. For example, if you have a database, in the past a database would be installed on one server and the storage attached to it, and it's a one monolith unit and you cannot decouple it. Today's modern architecture about databases is the compute is separate and the storage is separate, because in the big data world there are many types of use cases. For example, a lot of data, minor compute jobs, or the other way around. For instance, data science, you need 1 month of data, but a lot of compute, something that takes days, weeks, depending on your training. So decouple what you can, and as a rule of thumb, try to keep the amount of technology stacks between 3 to 7 to simplify things. Otherwise, it's very hard to maintain and you need a bigger team and so on and so forth. So we talked about, first thing is the use case. Let's talk about the use case here in Voila. If you don't know, I am currently working in Voila. I joined Voila team about 2 years ago. We created a company called BU. The idea was to create a platform that enables data collection from many data sources and to derive insights from it. The type of insights are based on the use case. So let's talk about the first use case. The idea was to analyze browsing history of users. Imagine an ISP, and we want to generate marketing insights about intent of users. For instance, someone is going to booking.com. That means he has a travel intent. So let's put an advertise, buy a ticket from us. Okay, that's one use case. The challenge there was the velocity of 1 terabyte per day from data center to the cloud. The second use case was deriving location-based insights. It was an interesting use case because it was collecting data from the core network of a mobile carrier. Okay, that means you go to the data center of the mobile carrier, you put your system, you get a copy of the network into your system, and the velocity was 4 gigabytes per second, which is about 40 gigabits per second. It was a bit challenging. We had to create out-of-the-box thinking and architecture to resolve this. We did it. We created a proof of concept. This project did not go live due to legal reasons, but the technology was there. Third use case was analyzing location-based events. The idea was to have mobile apps that constantly send location data to our platform. The challenge there was to minimize the DevOps work to a minimum because we didn't have a large team to maintain a large ingestion platform. So basically, what is the product we tried to create? The idea was to create a generic big data platform on the cloud that collects data from different data centers, analyzes the data, generates insights, and the idea was to present it in a report or communicate with marketing solutions. The customers were either marketers or publishers or agencies, so basically this was the company's purpose. My big data platform was about collecting data from online sources, Alan, and offline sources. It had to do some transformation to take one format of data and transform it to another format, to model the data via different technologies, to visualize it, and to handle regulation. Basically, if you put it in a nutshell, it was about performance, cost, security, simplicity, and best practices. So if we take all that we discussed and put it in one simple diagram, if there's one take-home message, I would like you to remember this slide from the entire thing. The idea was to create an architecture that is as generic as it could be, and each layer can be replaced in the future should a better technology arise, should a far simpler, far cheaper solution would pop up somehow, because the ecosystem keeps changing. So what we have here is the layer of the data collection. So basically it's an ETL of files that goes all the way to S3. Even if I had events here, I would capture them here and transform them into files before shipping them outside to avoid problems of network bandwidth, which is quite limited for me as a provider or integrator. So the challenge was to handle the velocity at the edge and make sure the data goes into S3, naturally in a raw format. These slides will be available for you. You could download them later. You can take pictures freely, but just know everything will be shared. So that's it. The rest, what we are going to do in this lecture, we are going to drill down on each layer. So bear with me, we'll start from this layer and go up. Okay, but be sure to understand that each input and output of the layers goes through S3, which is the storage solution of AWS. Please, please, please ask questions, and every term, every solution, every product that you're not aware of, please just shout, raise your hands, do something to make me clarify it. It's supposed to be very simple, very easy to understand what I'm trying to say. I'm not trying to deep dive in too much, but still explain the process. So let's talk about the data collection layer, the layer over here. The idea was to collect data on a batch way, in just moving files from one way to S3, and to create a generic. So in order to do that, we created a generic Java ETL tool that takes the data and applies transformation filters, for example, removing rows, removing columns, encryption, grep, replace strings, anything that the legal team would ask us to do. Once we arrive at the data centers, I don't always know in advance what's going to be. Sometimes things change on the last minute. Sometimes you do something and then you lose the access to the data centers. You need to be able to tell your data source provider, just change the command line like this and everything will follow. So the idea was to work one time to create a Java-based ETL tool that does all the transformation features and handles the performance requirements from all the different types of data sources. And we used the AWS Amazon Kinesis platform for ingestions of events from the mobile devices. Again, the output would be S3. So batch data collection consideration, just to give you some data, we used the velocity was about 30 gigabytes of compressed CSV files. We use S3 because it uses multi-part upload, which is a convenient way of splitting the file for you and utilizing the network faster. S3 has a built-in CLI tool which simplifies things if you don't have to do transformation at the edge. And it has an SDK so we can integrate it simply with your application. Don't forget to gzip or to apply any kind of compression to make your upload much faster. Why a client? We choose a client because it has to work on a remote server which we don't have access. It's not controlled by me, so it makes more sense to send the client, the data source provider, a client with some set of instruction, fairly simple. But just for general information, it's not recommended to implement your own client unless you have some specific feature set you need to implement, and there's a lot of uncertainty around it. So because code usually implies bugs and maintenance, and you usually don't want to analyze things at the edge unless you have some regulation restriction. Why not streaming? You had to consider why not do everything on streaming. First of all, it's less accurate. You can lose stuff if your ingestion platform falls, and it's much more expensive to do streaming. So if you can avoid it in 1 second, if you can avoid it, if there's no business justification for it, just keep it, please.
What is the data that you save on the 30 gigabyte?
This was the use case of browsing internet browsing history. So I got the log files of who served to what destination URL, about 30 gigs. Imagine a firewall of internet of the country. Now take the log file each hour, that was the output. From that you need to take only what user, or let's say source IP, destination destination URL. That's it.
And do you do all of it on one machine? Decompression? You get all the data?
Yes. So the question was about what type of use case and do I do everything in one machine? Yes, I took a simple server with 16 cores and 16 gigs around that metrics, and I did some efficient code, and I was able to accept the file, take it into memory, apply the transformation, read it, write it after it's compressed, and be within the time constraint that were defined. In this way you can process about 200 gig uncompressed, which is about 40 gigs compressed. Does that answer your question? Thank you.
You mentioned the importance of when you need the insights, like per minute, or what in this use case, how often did you need to deliver?
So the question was about when do you need, what do you do when you need the insights faster? Let's say.
I'm just asking what was your, did you need it on an hourly basis?
Oh, so my time constraints were 24 hours. I didn't need something faster. The next day was good enough for our use case. The entire use cases I shown before. Yes, even the streaming parts, but only because I got it in streaming, so I had to handle the filter in flight, remove the junk, only take what I need, apply the transformation at the edge. The output was very small, so there was no need to send it every minute. And there was no business justification for it as well. Just so you know, I repeat the questions only for the video, so people that watch the video will be able to know what was asked from the audience, because the camera doesn't hear you guys. So the S3 consideration in terms of security has all the security features you would expect. If it's encryption, which is managed, you can do some encryption in transit, and you can do some hardening, meaning you can, 1 second.
You lost the speaker.
Yeah.
You can't hear me?
We can hear you. Record you.
I'm not sure the recording works.
The speaker's not working.
The speaker is not working?
No. And we're not sure about the camera either.
The camera hears me. I can see the decibels.
Oh.
If you can hear me, that's okay.
Yeah, okay.
Alan.
Okay.
Okay, so S3, just let me finish the section and I'll get back to you. So you can harden everything in S3. You can restrict user, you can restrict IPs, and create an access list, and you can do some crazy stuff like give only write permissions to users. So if I'm writing something from a remote database which is not controlled by me, I give a user which has only the ability to write, not to read, not to delete, not to do anything. And please.
You didn't store your source data. I mean, you didn't use any data lake or anything. You just extract everything that you need, and that's it.
On the data collection layer,
It's not working. So.
on the data, sorry, a bit excited. On the data collection layer, all you worry about is collecting the data as fast as you can and as legally as possible in terms of security, in terms of restriction, and passing it to the next year. You don't worry about anything else.
So you didn't store your
On the data collection, you cannot store because it's not the purpose.
No, I understand, but the question, you didn't store your source data in any way. I mean, for the future, you want to do something else with the data.
So the question was about storing data for the future. Yes, I store it, but after I collect it in S3. So in S3, I keep it for future references if I made a mistake to go back in time, apply some jobs, and so on. But on data collection layer, whatever I collected, in, out, in, out, in, out. Furthermore, the legal restriction specifically say whatever you collect, you're supposed to delete at the edge. Okay, and you have some limitations on what you can keep and how much you can keep. Okay, on the upload section, again, the AWS S3 CLI allows you to do some multi-part upload, which is very nice. You have a sync command, which allows you to sync files if you're not sure what you moved. So one of the tools we expected was Scoop. It's part of the Hadoop ecosystem. It's a tool that allows you to do some ETL. The reason I didn't use it is because I didn't have access for a remote database. All I had due to restrictions is a data center, and all I needed to do is put my app on a server and wait for a file to be pushed to me. Didn't have access by pull. So a nice tool like Scoop, it's usually good for when you have databases and they are controlled by you and you want to create some ETL, bidirectional ETLs. Flume of Kafka. Sorry. Flume and Kafka, open source solution designed to handle this layer's purpose, which is data collection. They are very known tools. The downside is DIY, do it yourself. You have to have someone in your team that will have the skill set of managing a Kafka cluster, which requires a bit of a learning curve. Same goes for Flume as well, but it's a bit simpler. It has many connectors. Even Kafka has many connectors, but the learning curve of Flume is a bit simpler. Please. So I didn't use this. By the way, notice the V or X on the right. This signifies what I chose or didn't choose for my platform. So the idea is to review the technologies available at that time that I knew or people recommended, did some research on it, and took this as advantage, and decided go, no go on this technology. So in terms of data transfer options on AWS, there are many options. One of them is Direct Connect, which is physical cable from the remote data centers all the way to your data center in the cloud, which could be anywhere in the world. I didn't choose it because relatively expensive, and it's good in terms of performance, but it doesn't make sense to create a direct connect per customer DC. It takes a lot of time. It's like heavy-duty machinery. VPN, managing site-to-site VPN is a good option, but again, managing VPN site-to-site from your cloud to any customer is a bit crazy. So
How many customers you are talking about?
At the beginning, we talked about 10 data sources. Data sources, not customers, and the customers would be scaling over time, so I didn't want to do this. So for our intended purposes, S3 was good enough simply because of the security and the ability to transfer data easily. Bandwidth was a huge problem for us because of the velocity. We had to make sure the customer has enough bandwidth that matches the use case we're trying to implement together. Stream collections, there's the Kinexys client library, which is writing code. There's the AWS Lambda, which is serverless architecture, again, writing code that does many things. EMR, which is managed Hadoop, and a third-party solutions like Spark Streaming, Storm, Flink, which again, the downside is do it yourself. Everything marked with red, naturally I didn't choose. The green I took, which is managed EMR, and we'll talk about it some more. Kinesis. Kinesis is a family of products in AWS Cloud. The idea was to collect and do some near real-time processing, to have a high throughput, and you can deliver it for many destinations inside AWS, like S3, Redshift, Dynamo. The ingress rates may differ. The downside, it's not managed, at least compared to Firehose, which is quite simple and you don't have to do anything. Kinesis Analytics allows you to do some in-flight analytics. We use that to do some filtering for eventing that come into us, but now after a while we removed it, so it should be red, but I forgot to fix this. You know what, let me fix this 1 second. We are quite agile. Boom, fixed. So what we used in the end was Firehose. Again, this should be green. Firehose, which is as simple as one can hope for. You simply define a service, you ingest data and it saves it to S3. The downside, it's not a fast lane, meaning it has a window of 1 minute when you cannot apply in-flight analytics on it, which is the service we discussed. But you can send it to the next layer easily, and you don't have to worry about this. So I installed it once, set up the configuration once, and I didn't touch it ever again. The simple comparison, the Kinesis streams is more about, call it sub-second processing latency, and Kinesis Firehose is about 1 minute buffering and 0 and win. And you have some 4 built-in targets, and it can handle larger events than Kinesis streams. So this is the logo of Firehose. So we discussed the data collection, and now we're done with this. Questions? No. So we are moving on to the next layer, which is the data transformation. We chose EMR for that. The reason we chose EMR because it has the entire ecosystem of Hadoop managed in AWS. It's an AWS distribution. Has Hive, Pig, Hue, Spark, Uzi, Presto, Ganglia, Zookeeper, Zeppelin, and probably some other stuff I forgot. And we're going to discuss about them. So let's talk about a little bit about the EMR architecture. It's like the Hadoop distribution, it has a master node that saves only the metadata. The metadata of the files, and the files itself are kept on the core nodes, which are have both the compute, the CPU, and the storage, which is distributed, i.e. HDFS, Hadoop file system. The idea in Scaleup Architecture of Hadoop that you have one server that manages the metadata, and all the nodes have a specific chunk of the data, and you can apply jobs on it, and has the matching compute resources to do the compute on the data. And if you need more compute power, you simply add more nodes. The downside of it, compared to the normal distribution, is you don't have a standby master node. That means that if your master node dies for some reason in production, you lose all the associated data with it. There's no way to recover from this. Okay, so just be aware. It's not a major disadvantage simply because the EMR architecture is mostly designed for transient cluster. That means they go up, they do the jobs, and they go down, and you keep the data on S3, and all the metadata is stored externally, so you don't lose anything even if the cluster is deleted. Okay, so that's the best practice. This is why it's green, so the red is not very significant. Lesson learned about EMR, generally speaking, before we go deeper. The idea of Hadoop was in the beginning, let's use smaller servers, but lose thousands of them. If you are missing resources, just add more, okay? But as time went by, I realized that maybe we should go back to the original version of architectures where we consider the scale-up architecture, where we put more CPUs, more RAM, more network, more disk per machine. That way the maintenance is quite easier, and it's much easier to understand. You have a cluster of 10 machines, not 1,000 machines, but there's a linear growth per machine. Instead of 1,000, use 100, which is 10 times bigger, for example. Okay, we use
better for a human being because you want to.
Both.
Is it
Both.
to you to manage it? Or
Both.
both?
Is
And financially, the cost of
the financial
100
is.
big servers and 1,000 small servers.
So the question was about better for a machine or better for a human, and about the cost. So yes, it's better for both. It's easier for a machine to handle 10 machines because it just gives them a bigger job instead of a smaller job and managing the overhead. This is one thing. And for a human, it's much easier to understand because it's really easier to track the monitoring of the cluster and understand what is happening in your cluster. Why is it failing, and so on and so forth. In terms of cost, let's keep the simplified version. Yes, it's the same cost because it's linear. If you take 2x machine in terms of resources and you take 1x machine, the cost is linear between them. Okay? Yes, there's a slight asterisk of מה שנקרא סוגריים, but basically the same. There's many compute engines for Hadoop ecosystem: Tez, MapReduce, Spark. The latest in EMR currently is Tez. The old one is MapReduce. We switch sometimes to MapReduce, which is older, but it works better. The Spark as a compute engine, for example, Spark under Hive is not supported, which is something which is very useful. I would recommend choosing instances which are more expensive simply because the network is upgraded, and this is a bit over the price. I mean, if you double the resources and you double the price, but now you didn't double the network, so in the price, so you get more for less. Was I clear? Smaller machine, smaller network. Bigger machine, much bigger network. Okay? You can do some resize to the cluster, mostly up, down. I had some bad experiences, but I was told it's working perfectly. But I didn't have good experiences with this. You can do some bootstrapping, some steps to automate your cluster and do many cool things that go up during the night and run some nightly jobs and your cluster. Good on times. Okay, and you can use Glue as an external meta store to store all your metadata outside, and this is where you can remove the cluster. Inside EMR, the dominant technologies are Hive, Spark, and Presto. And the use case is mostly for data transformation, data modeling, batch, and machine learning. Yes, you can do sparse streaming with this, but it's not managed. I used Hive and Spark SQL. Okay, and Hive architecture. Hive is a database. It's a SQL database that works on top of HDFS. The idea is that the client works on top of an engine like MapReduce or Tez and does the calculation after getting the data from the Hadoop file system or from S3, which is the storage of AWS. This way, when you remove the cluster, all your data and your metadata are outside the cluster. Hive, as we discussed, is all about SQL, different type of the engine. You can connect via JDBC, ADBC. The downside of it is it's not good when you need to shuffle, i.e. Move the data between nodes. It's not for petascale, but it has the flexibility to process a variety of data. It has dynamic partitions, keep this in mind, and insert override. It has the ability to transfer data easily and a lot of flexibility, and mostly used to convert to Colo now. Presto has many good things and has evolved a lot lately, but at the time I needed the insert override and dynamic partitions. There's a blog here with all the There's a blog here I wrote with all my conclusions when I researched Presto for our needs. It's in the website we discuss. It's over here, you can read it if you like. It's very deep, so I won't go into this in this lecture. The idea about insert override was if we make a mistake in the past and want to fix a specific portion of the data, partition portion of the data, you can do it easily, and the complexity overhead of managing the jobs is quite simpler in Hive. So this is why I didn't use Presto. Pig is another solution by Hadoop, which we didn't choose part of EMR. It's a distributed shell scripting. You can do some simple operations on your data, which will work on your entire cluster. It's good for people who don't know SQL. Hue. Hue is, as you can see here, it's a GUI, a web GUI, part of, again, EMR distribution that allows you to write SQL queries on your databases. For example, Hive, this is one way to communicate with Hive. It's a query editor, simple, has many features, it's a good starting point, it's out of the box. You launch a cluster, log into the GUI, and you can start querying your data without installing anything besides your pressing click on start cluster. Uzi. Uzi, again, another solution within the Hadoop ecosystem within EMR. It's a tool designed to do only one thing, orchestration. Should you have many jobs, you need to trigger them in specific hours, in specific order. There are many other tools where I examined at the time: Airflow, Nime, Luigi, Azkaban, AWS Data Pipeline. They each have their own advantages and disadvantages. The reason we chose Uzi in the beginning was because it has both GUI capabilities, drag and drop, both API, you can send requests from code, and you can do it from the command line as well. So basically, if we describe again the transformation layer, we use Hive, which behind it consists of some services like Yarn and HDFS and Tez and Hue and Uzi. Any questions about the transformation layer, please?
What's this?
Tez, if you recall, I briefed quickly through it. This is the architecture of Hive. Hive is a database. The idea was that you have a client that you write the queries, you send it to an engine, and then you collect the data. So the engine, in the entire Hadoop ecosystem, the engine can be replaced. Instead of MapReduce, you can put here Spark, you can put here Tez. The default is Tez in EMR, but you can change.
When you use Spark, it's simply...
No, if you use Hive, you are using in the background engine called Tez. But you can do select engine equals MapReduce, something like that. And that's it. Question about transformation layer. Okay. Next layer is the modeling layer. This is the crux of the system. We usually, in the beginning, we used Amazon Redshift, which is a simple, veteran PaaS architecture solution for database analytics, like Teradata, HP Vertica, and so many other solutions. Spark SQL, Zeppelin, RStudio, Drift, Giro, and Livy. Again, most of it, all this is part of the EMR. It's just not very highlighted in the AWS marketing, only in the, if you read the documentations in details. So Spark, again, architecture decoupled. You have many APIs over here, Spark SQL, which is what we use. Again, like a database, you write simple SQL queries, you run in memory on the Spark engine. You can use the data, take the data from a resource manager called DR, same like Hive, or you can take it directly from the file system. The reasons to use Spark, it's compared to Hive, it's in memory, it's sometimes 10 to 100 times faster, has a good optimizer, rich API, you can do many other things besides SQL, you can write code, you can do machine learning, you do graphs, and you can connect to R, which is one use case we applied here. The Spark streaming, you can do really cool stuff, it was very popular at the time. We didn't need it for our use case, so I'm not going to talk about it, just for completeness purposes, it's here. Spark ML's machine learning library we considered at the time. We used it a little bit, but we switched to SageMaker later on. There's a lot of flavors for Spark, so it's quite confusing for completeness. I put a slide on top. You can run Spark as a whole unit without deciding the compute engine, which is MapReduce or Yarn, okay, and resource management. So there are 3 different options to run Spark. For instance, standalone, which is quite popular for developers. And you can use some resource manager called Mesos, which is another huge, massive open source resource management solution. But in EMR, the default is Spark over Yarn. The downside, there's a different behavior, although it's a different syntax, the Spark, SQL, and the Hive. There's a different syntax, the same syntax, but the behavior is different. For example, in the past, there was a problem with the insert overwrite. In Spark, it will delete other partitions as well and start from the beginning. In Hive, it only will overwrite what you told them to overwrite, which is one difference, and there are more. Why we chose Spark SQL? Because it has the same SQL syntax as Hive. It has optional JDBC, so data scientists can work on top of it without knowing what is the engine running behind it. It's faster than Hive, and it's out of the box connected with Zeppelin, which is another GUI we can discuss. It's this logo. It doesn't replace Hive. It's not always faster than Hive, but the Spark is usually faster, but some cases it's the other way around. Not supported on partitions. It's no longer true. This was sent a comment that this was fixed from version 2.32. Zeppelin, again, yes, please.
Can you extend a bit about the distinction between the use of Spark as
Yes. Hive was designed to do some batch heavy duty jobs that will run days, hours, weeks. It was not designed for ad hoc query, meaning there's a lot of overhead in the beginning. We send a query, take a few seconds for warm-up, deciding what to do, and going to this, saving intermediate results to this, so it's much slower by design. Because if a ETL job fails, which is very long in the middle, you don't want to start from the beginning, you want to start where it's stopped. Okay? In Spark, if a job fails in the middle, everything is in memory, so you lose everything and you start all over. So it's all about use case. So Hive, when you have a batch ETL heavy duty job, use Hive. When you want to do some ad hoc query research for data scientists, Spark SQL, buon buoniera. Okay, good questions. Please keep them coming. Zeppelin. We had a restriction. We could not allow users to work via JDBC from their laptop to connect to the platform because I need to open firewalls and ports and stuff like that. So we gave them a web GUI. And that web GUI was supposed to be out of the box, simple, with no configuration, with user management, permissions, collaboration, you name it. Furthermore, this tool has the ability to visualize, meaning you write your SQL and you get the result and you press a click and you get a graphic instantly, so you can analyze what you see.
Like Redash?
FreeDash?
Redash.
Not familiar with. Redash? Yes. Okay. Notebook, like forgot the other name. Jupyter, yes, thank you for that, Jupyter. The benefit of Zeppelin, you press a click, you have an EMR cluster with Zeppelin connected to a Spark. Within 5 minutes, you can start querying your data. Simply. In the background, there are two open source projects called Shiro and Livy. Again, part of the distribution, nobody talks about it, nobody knows it, unless you read the documentation. Shiro is about security, groups, permissions, data engineering, data science, and some sort of permissions you want to manage. And Livy is about the ability to work on a remote cluster, meaning you have a data scientist with R installed on his laptop and he wants to connect to a remote cluster. Livy is the solution that enables it, because all the tutorials you see require both the RStudio and the Spark to be on the same machine, which is a bit of a problem.
In the kernel.
Kernel? Meaning what?
Never mind. But that the IDE can be detached.
Yes, the idea is the IDE can be detached. Livy is the open source project that enables this. Thank you for your comment. So, R and Spark R. Spark R is an API on top of Spark that enables you to run your R jobs on a distributed cluster, which allows you essentially to outgrow your R machine's RAM. For instance, you have a job that requires a lot of RAM, you simply send it to a Spark server with enough machines, and you are done with your problem. This was a valid use case as we used it. Redshift. We started using Redshift in the beginning for simplicity, simply because this is what the data scientists knew. But there's two downsides to using Redshift. One, you cannot kill the cluster easily. You can do it, but it takes a lot of time to go up and down, because you need to insert the data and export the data back and forth from S3, which takes time, especially if you have a lot of data. But the new paradigm, working with external tables, meaning the data is kept on top of S3, the metadata is kept outside of your cluster, so all you have to do is turn off and on your EMR cluster and you have the data. You can simply fire up a machine and start querying the data, and in Redshift you need to fire up the cluster, migrate the data and start working, which is costly and not time efficient. But there are a lot of advantages for it. It's fully managed, it's fully ACID, supports a lot of SQL features. You can do a lot of things. It's good for complex joins and data warehouses. It's a good practice solution, but again, depending on your use case. We didn't choose this. Redshift Spectrum is a new addition from the last 18 months ago, I think. It enables the Redshift users to access data which is stored externally on S3 and not do insert and then query data. Has many advantages, but also many disadvantages. Doesn't allow you to create as a lake. Complex data structures are not supported. Not very recommended to do joins on external data. It's good for read-only queries, for aggregations or large-scale data instead of insert it into your cluster and pay for the size of a cluster, which is limited to the amount of disks on the nodes. EMR versus Redshift. Many questions you should ask yourself. It's the amount of data you need to load and unload each time you work with a cluster. Do you need it 24/7? What type of operations are running on top of your cluster? Are you recycling the same data again and again? Are you analyzing history? Are you creating a data warehouse, a BI? Maybe you need some aggregations on large-scale data. Maybe you have some raw data, so keep it in. So it's very confusing. There's a whole blog about this I put in the website. What happens for Hive versus Redshift? When you need a low amount of concurrency, use Hive because it's for jobs to run during the night, not to handle a large-scale data science team. If you need a high amount of concurrency, use Redshift. If you need customer access, use Redshift. It's the fastest, more or less. You need to transform data, use Hive. You need something which is better scale, use Redshift. Complex join, use Redshift. So again, what you see is simple example, simple answer to simple question, when do you use which technology, and so on and so forth. So this covers the modeling layer. The next layer is quite short, the visualize layer. What you see here is Amazon Athena, ClickSend, and QuickSight. Athena is a relatively new service that allows you to run SQL on top of data on S3. Meaning, remember the diagram of sending data from the data center? I put it in S3. Once I put it here, imagine for a second I don't have these layers yet. I can start querying the data immediately. This saves a lot of time and effort, but has some disadvantages. So if you want to benefit from it, you need to convert it from raw data in row-based format to columnar-based format. It's good for read-only SQL because it doesn't have insert. It's very nice when you want to do ad hoc query, if we discuss this. It's very low cost, like $5 a terabyte. Some customers pay like $2 a month for using Athena, which is nothing compared to the alternative. And it's completely managed. You don't manage servers, you don't have to worry about uptime, nothing. Visualizing. AWS has a new solution called QuickSight. It's relatively basic, but if you have some basic dashboarding you want to do, instead of buying a top-notch ClickSense BI solution or Tableau or whatever, you can start working with QuickSight for like $10 a month and get something basic relatively quick within the hour. So summary, what we have here, generic big data architecture that covers a lot of use cases. We have Scoop here for completeness, but I didn't use it for ETL purposes. Java for our client that did the ETL on the customer data center. The entire Kinesis family for Firehose, streaming, a complete separate decoupled layer called transformation. I used Hive and Hue on top of it to visualize what I'm doing and use it to orchestrate the jobs, sorry. Layer on top, data modeling, used all these technologies. Eventually, I got rid of Redshift for two reasons. One, costly. Two, the syntax was different from Spark and Hive. So imagine a data scientist working on Redshift, data engineer working on Hive, and now when they want to pass jobs between them, they need to work on migrating the syntax and dealing with all the failures, because one is not working in the other technologies. So when we removed that and asked politely the data science to work with Spark SQL, the syntax was the same. We reduced a lot of time between and overhead between the teams. So it's very important to consider that if you have separate data science and data engineering teams. Sorry. So lesson learned. So we discussed now the productivities. The moment we removed Redshift and considered using Spark SQL and Hive, we increased productivity and communication between data science and data engineering. All the time lost was removed. The bridges Spark has gave us many ability to grow in future data science requirements like Spark R and Spark ML once we considered Spark. In the beginning we only used Hive, we didn't have Spark, and then we added it. I highly recommend to minimize the amount of database use simply because of the different syntax and different data types. For example, complex data structures, which are commonly used in Hive, are not supported in Redshift, which is a problem. If you get it in your data, you won't be able to process it easily. Not always streaming is justified. Consider the business use case, consider using pass. If you don't need the data less than a minute, Firehose will be very good for some basic use cases and maybe even more. Spark SQL, sometimes faster than Redshift. We did some benchmark, which was surprising to find out because under documentation it's a bit slower than Redshift. Sometimes it's slower than Hive. Learning curve is not trivial, but we found it very important and very useful to do this. Takeaway message, besides the slide and the layering decoupled, is this. Smart big data architecture is all about doing things faster, cheaper, simpler, more secured. Imagine a good data engineer and a bad data engineer. The difference would be that in the end of the month they will both do the same job, but the monthly bill in AWS would be 1 to 10 in costs. So if you invest in a good data engineer, big data architect that really knows what it is doing, really knows how to select the right technology for the right use case, consider the company cost, not take a 1,000 cluster EMR or 1,000 cluster Redshift simply because that's what everybody is doing, you may be saving a lot of money. Each mistake a data engineer does has a vast implication on architecture, thus vast implication on monthly bill. There's a lot of articles I wrote about cost reduction in the website. We can I discussed them in some other meetups. So to conclude, I just want to say thank you. This is the links for the website, my meetup. Thank you for Asaf for hosting me in his meetup. There's a YouTube channel with some movies from my previous lecture if anyone is interested. If it helps, it's for free. And that's it. So if you have any questions, please, now is a good time. No. Okay, so thank you very much for your time.